My name is Alexandra Albu. I am a first-year PhD student at Babeș-Bolyai University, and I am working in the OMI project. And today I will be presenting some preliminary results obtained so far in our project with using deep learning models for predicting radar reflectivity values with a certain or with a specific focus on composite reflectivity prediction. This is an overview of my presentation. I will start by briefly presenting the computational approaches proposed in the nowcasting literature so far. And then I will move on to presenting the results we have obtained with two of our models. Then I will present the conclusions of our work so far and future directions of research. Among the computational approaches for nowcasting, two of the main ones are numerical weather prediction methods and optical flow algorithms. But in this presentation, I will mainly focus on deep learning approaches to the nowcasting problem. These methods provide a purely data-driven approach to the nowcasting problem in the sense that they make minimal assumptions about the physical system being modeled, at least in their traditional formulation, and instead learn patterns from the data itself. They do this by modeling the nowcasting problem as a spatio-temporal prediction problem, and thus they make heavy use of convolutional and recurrent neural networks. These type of deep learning methods basically learn a mapping from weather states at a geographical region, at one or multiple timestamps in the past to the weather state expressed as either measurements, observations, or composites, derived products at that geographic location at one or multiple timestamps in the future. The deep learning approaches can be broadly split into two categories based on how they handle the time dimension, the temporal dimension. The first category is composed of recurrent neural networks, out of which the most used one was the convolutional LSTM, which is a type of LSTM in which also the spatial dimension is taken into account by introducing convolutional operators inside the LSTM cell. And also its more recent version and improved version, the trajectory GRU. The second category of approaches are those using fully convolutional neural networks, which are mainly inspired from segmentation models such as UNet, but also using concepts from the video prediction literature, such as 3D convolutions or causal convolutions. Basically, training neural networks boils down to an optimization problem, and such networks are actually trained by optimizing various loss functions, including traditional pixel-wise losses, such as mean squared error, root mean squared error, or mean absolute error, or various similarity losses, which try to better capture our perceptual similarity of two images, but also various versions of weighted loss functions. Among the challenges and big limitations of current deep learning models, at least in the nowcasting scenario, is the fact that they tend to underestimate high values, which is a quite big problem in this context because usually high values for the radar products corresponds to severe meteorological events, or at least meteorological events of interest. And this is a bit difficult. This problem is caused by the fact that our data sets are highly imbalanced, which makes learning patterns from these data pretty difficult. Another problematic aspect is the fact that at least when training with traditional methods, they tend to produce blurry predictions. Again, a problem which is rather technical is the fact that when having large geographical regions, it is difficult to obtain predictions all at once for the entire region. And another big limitation that has been also previously mentioned is the lack of interpretability or explainability of deep learning models in general, which is an impediment for actually using them in decision-making processes. The aim of our research is to improve the weather nowcasting solutions using deep learning techniques. And further, I will be presenting two approaches developed in our project so far. AutoNowP, which is a binary classification model, and another model based on the exception architecture that is a deep encoder-decoder architecture. The experiments I will be presenting have been performed on radar data that is publicly available on the MET Norway THREDDS data server. The data that I have used so far contains composite reflectivity, as well as, which is the main or a very important reflectivity product available on the MET Norway THREDDS data server, as well as some preliminary incipient results with using base reflectivity values, which are the raw values that are being used afterwards in order to build the composite reflectivity data product. This is a visualization of the composite reflectivity data product for one timestamp, and it is overlaid on the map. This is a visualization taken from the MET THREDDS website. Now, I will start by presenting our first approach, which is AutoNowP, which is a binary classification model that predicts whether a point will have a value greater or smaller than a given threshold using the information contained in the neighbors of that point at the previous timestamp. It does this by using two convolutional autoencoders, one for each of the two classes, below or above the threshold, and each of the two autoencoders are trained to learn the characteristics of that specific class that they are being trained on. This is a schematic overview of our approach, including the process of splitting the data points into positive and negative instances. From now on, I will call positive instances those data points that have a value greater than the threshold, and negative instances those points that have a value below the threshold. And after this process of partitioning the data set, we can train the two autoencoders, one specific for each class. And the last step involves presents the classification process, which consists in taking a test data point, passing it through the two autoencoders, and seeing which of them is able to better recognize it. So these autoencoders are neural networks that are trained to reconstruct their given inputs by compressing, as a first step, the input into a low-dimensional representation, low-dimensional space. And in this way, it is expected that that autoencoder is able to learn the most important characteristics of those data points. So in this way, we take a data point, we reconstruct it through both of the models, and we see which of them is able to get a lower reconstruction error, meaning that maybe it has recognized in that test data point some characteristics that it has previously seen during the training process for its specific class. This would be the general idea. Now, one issue that we have observed is that when taking points, it may happen that positive and negative points have overlapping neighborhoods because they are closely situated on the map. And in this case, both of the two autoencoders are able to properly reconstruct that instance. However, this is not what we would want. So in order to alleviate this problem, we have used different loss functions for the two autoencoders corresponding to the two classes. We did this by introducing a parameter, a weight parameter, let's say alpha, that controls how much errors corresponding to values above the threshold or below the threshold are penalized in our loss function. So using this parameter, we can make, for example, the autoencoder trained on the positive class uh, to better reconstruct the neighbors of the points that are positive, so the positive neighbors of the point, while the negative autoencoder is able to better reconstruct the negative neighbors. So in this way, even if the two autoencoders receive the same neighborhood, they treat it in a different way. And so they are able to better identify the correct class for that specific point. We have performed experiments for data belonging both, coming both from Norway and from Romania, but what I will be presenting in what follows is our experimental results with the composite reflectivity gathered from threads. And this table shows some statistics of the data set used in this particular experiment, the number of instances, and the number of positive and negative, the proportion of positive and negative instances for a threshold of 10 in this particular case. In order to evaluate our model, we have used multiple evaluation metrics. Among all of these, the first three are the most frequently used in the nowcasting literature in order to evaluate machine learning models. This table presents the results obtained for our method using a cross-validation evaluation procedure and for multiple thresholds. And we can see that the performance decreases with the increase of the threshold, which is to be expected since at higher thresholds, the classification process becomes more difficult and also the dataset becomes more imbalanced. All right, and further we have compared our approach with 4 classical machine learning algorithms. And we can see from the table that our method achieves the highest probability of detection and negative predictive value among all the classifiers. However, because we have observed a quite high degree of false positives, the other metrics are not as good as these two. This would conclude my talk about these classifier, and further I will pass on to the second model I will be talking about, which changes a bit the perspective on how we model the problem, in the sense that if previously for each point we have chosen a fixed neighborhood of points that characterizes that specific location, now we are instead giving the entire map, or at least a bigger portion of the map, to the network, and we are letting the network identify itself which points are of interest or are important for the classification or prediction process. This model is an encoder-decoder convolutional architecture, which is based on the exception architecture, which is an architecture which has been introduced in the computer vision literature, as Andre also mentioned. And its building blocks, it has the depth-wise separable convolution depicted in this plot. This is a schematic overview of our architecture. It does not contain all the architectural details like skip connections and other processes. Also, we have multiple versions of this architecture with various with some variations of the structure of the decoder and also other aspects about repeating blocks and stuff like that. But this is just to illustrate the main idea. And this is roughly the architecture that I have used in these experiments. It is an encoder-decoder architecture. The first part is the encoder that compresses the input or radar scan or image, if I can call it like that, to a low-dimensional representation, while learning more abstract and abstract features out of those input data samples. And afterwards, it reconstructs, it obtains actually the prediction at a future timestamp. So for the moment, this is a single-step prediction algorithm in the sense that it outputs only the map at one timestamp in the future. while being given as input one or multiple timestamps. So we can give multiple timestamps and overlay them on top of each other, concatenate them channel-wise, and give them as input to the network. And we receive a prediction, which we try to make it as similar as possible to what we should have received at that point. So in this way, it is a supervised approach. And this time we model the problem as a regression problem by using the root mean squared error loss. For the experiments I will be talking about in what follows, we have used both composite reflectivity and base reflectivity. For the first set of experiments, it is the experiments are performed on a data set containing 10 days with meteorological events. Gather that the radar values gather the time resolution of 5 minutes. And from the entire map that you have seen at the beginning, I have cropped a region of 200 by 200 pixels. The second set of experiments are a bit more large-scale ones, in the sense that we have included 321 days in these experiments and performed the testing on 40% of the data. This dataset contains base reflectivity on multiple elevations. For this preliminary experiment, I have used only the first level. And the time resolution this time is of 10 minutes. And also the square is a bit larger than in previous experiments. It's of 400 by 400, representing the center of the radar grid. This is a quick data analysis representation, the histogram of the values in the first data set. And we can see that it is highly unbalanced, our data set, and the small values clearly dominate the distribution of radar data values. Further, as a first step, we have performed an analysis of the impact of the temporal context in the prediction accuracy. Namely, we wanted to see how adding multiple past timestamps in the model influences the prediction accuracy. And actually, we have used multiple measures, so the critical success index, the false alarm rate, and also probability of detection for multiple thresholds again. These are some plots that show the actual metrics. So this is the critical success index for various number of timestamps and various thresholds. I have expressed here on the x-axis the temporal context in minutes to be able to easily see it. So we can see that the performance seems to increase up to 20-25 minutes in the past, while after that it stagnates or even starts decreasing in some situations or for some thresholds. The same type of behavior can be observed for the probability of detection metric. While for the false alarm rate, it's a bit more difficult to establish the optimal temporal context to be used, since for the large-scale experiment, it seems that using up to 30 minutes can still improve the performance for some thresholds. And also an observation is that, as we have seen previously, as the threshold is increased, the performance is drastically decreased. Further, I will present some sample predictions for the best models. So in the case of the first data set, by using 5 previous timestamps corresponding to 25 minutes, and for the second data set, 2 timestamps corresponding to 20 minutes in the past. And the first line shows the input radar scans given to the network. The second row shows our prediction, while the third row shows the ground truth image, so what we should have obtained. And we can see that they are a bit blurry, exactly how we would expect. And this is the same type of visual representation for the second data set. Again, on the first line, the input data, the predicted one, and what we were supposed to obtain. As we have seen, one limitation of the model is that the performance decreases for higher values of the threshold, meaning that the network fails to predict extreme values, which are, however, relevant for nowcasting purposes. So a possible solution for this would be to use a weighted loss, which puts more emphasis on the errors we obtain for high reflectivity values. A general formulation for such a loss would be the following. And it is somehow similar to the previous weighted loss that we have discussed in the context of the other classification model. But this time we take the entire range of reflectivity values and we partition it into intervals and use those intervals to define a step function, W, which assigns a higher weight for the errors corresponding to higher reflectivity values. So in this way, the network knows to put more emphasis on properly reconstructing or properly predicting, better say, the higher reflectivity values. And these would be some results, preliminary results obtained with the weighted loss in comparison with the classical root mean squared error. And we can see that for higher thresholds, indeed, using the weighted loss was able to improve the critical success index and the probability of detection metrics. However, at the cost of achieving a bit higher false alarm rate. In the lower thresholds, the metrics are a bit better for the root mean squared error. However, the difference is not big, and it would need a better evaluation process. So repeating the experiments and performing a cross-validation procedure to clearly establish if the difference between them is significant or not. So to conclude my presentation, accurate nowcasting of severe events is a very challenging problem, and most probably it requires use of very complex and elaborate deep learning techniques, as well as so both architectures and training methodologies. And as future research directions, we plan to extend our models to be able to predict multiple steps ahead, also something like at least 15 minutes, 30 minutes in the future. Also, a disadvantage of the weighted loss that we have talked about previously is that it introduces some additional hyperparameters, so the number of intervals, the weights for each interval, which have to be tuned in order to find the optimal value. So from this perspective, it would be useful to have an adaptive mechanism to find these values. Another direction that we'd like to investigate is to be able to quantify uncertainty in our predictions by being able to output a probability distribution instead of just deterministic predictions like we are doing now. Thank you.